Okay, so we were looking at how derivatives are rates of other types of functions other than just motion, velocity, and that kind of thing. We saw the marginal cost, we saw population growth, we saw the rate of change of area or volume. Okay, so we have those things there. But I want to actually look at optimization. We mentioned this term optimization. And can someone remind us of what we're trying to find here when we're trying to optimize something? Huh? The best solution for the situation, okay? Now, the best solution, when we're talking about best, guys, we're talking about a value that will give us either the highest or lowest. We're looking for either a max or a min, and this is important, on an interval. It may not be the absolute max of the entire function. In fact, the function may go off to infinity. But we're going to be identifying some interval, i.e. the domain of the function for that situation, that will then help us determine, okay, what's the maximum within this set of realistic possibilities. Okay? Now, those realistic possibilities may just be innately in the problem, or they may be certain constraints that we put on the problem. Okay, like if we're doing that area of a triangle one that we had seen before, we may want the area to be at least a certain amount. Or we want that angle to be at least 20 degrees. Okay, we don't want to get any smaller than 20 degrees. So within that constraint, what is our maximum area, or maybe even minimum area, depending on the situation. Okay? This is kind of a step-by-step process. We're not going to write out step 1, step 2, but here's the thing. If you're stuck on one, then go ahead and write out step 1, step 2, and learn the process so you can think through these things, okay? So first of all, if the problem allows for it, you want to draw a large, clear diagram of the situation, okay? Make a diagram, label it with the information that you are given, okay? A lot of times students don't want to write things down, and then it's a lot harder to be able to see what's going on in the problem and make the connections that you need to make to solve the problem, because you keep going back to the paragraph or whatever and trying to pull everything out of it, okay? So then the second thing is you need to ask yourself, what am I trying to optimize? Okay? It says, write a formula with the variable to be optimized as the subject, okay? Now what does that mean? As the subject, that means like if I'm trying to optimize area, then it's going to be A equals something. Okay? If I'm trying to optimize cost, then it should be cost equals something. Alright? Now, in order to actually be able to use it, it needs to be a function. So it needs to be in terms of one variable. You may not be able to figure that out initially right off the bat. You may have a formula you know you can use, but it has 2 or 3 or even 4 variables. That's okay, write it down. Your next task is then going to be to try to write all of it in terms of one variable. So how are these variables related? Can I say that, okay, I've got an x and a y, but I know y has to be 2 times as much as x. So now I have x times 2x, and everything's in terms of x's. All right? That's the kind of thing you have to do, okay? Then, since we're trying to optimize, the optimal point, max or min, is always going to occur when the derivative equals 0. Okay? It's when the derivative equals 0. Those, remember, we call relative max or min points, or local max or min points. Okay? Now, here's where the extra part comes in, and that is you need to identify the domain. Okay? The domain, because guess what? Your max or min may not be at one of the relative max or min points. It might also be at the end points, one of the end points. Okay? So the max or min can be when the derivative is 0 or at an end point. Where the derivative equals 0 or at an end point. So, once you figure out your domain, you need to test the values of the endpoints and of the relative max and min points and see which one is the highest or lowest. Okay? And then, of course, step 5, make sure you answer the question. That's usually the easiest step once you've done everything else, and a lot of times we forget and don't answer the complete question. Alright, so you got to be careful with that. So let's look at how this works, okay? So we have here a 4-liter container, must have a square base, vertical sides, and an open top. Find the most economical shape which minimizes the surface area of material needed. Okay? Well, let's first of all draw a picture of this, okay? It has a square base, so we have to kind of draw in 3D. So I'm going to make this kind of angled like that for some perspective. Here's our square base and vertical sides, okay? Alright, so that's a pretty decent drawing, okay? Now, what do I know about this? What am I told about this thing?
Open top.
Open top, okay? So when I'm calculating surface area, do I count both bases?
No.
No, okay? Open top. What else do I know?
It holds 4 liters.
It holds 4 liters, okay? Now if it holds 4 liters, that means that's a measurement of what? Liquid, okay? Or yeah, anything that it's holding. So what do we call that in terms of measurements? It's not a distance, it's not an area, it's volume, okay? It's a volume. So here, notice here, this is a volume, is 4 liters, okay? Now, I have a little conversion here because if we're talking about lengths and distances and areas, I need a unit of measure that is related to lengths and whatnot, okay? So 1 liter is 1,000 milliliters, and a milliliter is a cc. You know, like if you've ever had a IV and it's like so many cc's of fluid or whatever, those are cubic centimeters or milliliters, okay? So this is 4,000 cubic centimeters, okay? Now notice the cube is just cubic centimeters. It's not cubing the 4,000 here, that's just a unit of measure. So, we want the formula for the variable to be optimized, but there's one more thing about this picture that we could identify, and that is that the bottom is square, but we don't know how tall it is, right? So let's go ahead and label this. I'm going to make these both x, just so that they're both the same length. And then what do you want to call this side?
Q.
Sure. Okay. Q. It won't be around very long anyways. That's okay. All right. So here we have x, x, and q. All right. So now we've got to think here. All right. What's the formula? What variable am I trying to optimize? Surface area. Okay, so surface area. How do I find the surface area of this box over here?
As always does. I have no idea. That was the
Well, come on, guys. What's this box made up of? Sides. What shape are all the sides? Squares or rectangles. Can you find areas of squares and rectangles?
Yeah.
Yes, so you can find the surface area. Come on. So the bottom, what's the area of the bottom?
XX squared.
X squared, okay. And then, what's the area of one of these sides?
X cubed.
And how many of them are there?
4.
4. So guess what? It's 4x cubed.
Wow.
There you go. There's your surface area. All right? Listen, one of the downsides to taking geometry is we forget to think. And we think that if we don't memorize the formula that we can't possibly know how to do it. All right? You know what surface area is. So just figure it out. We don't need all the formulas. Okay? Now, this is where we don't have a function yet. Okay? We don't have a function yet. Stay with me here. In order to have a function, I need to have this surface area written in terms of only one variable. So I need to substitute out the q. And that's where the volume comes in. There's going to be if you have more than one variable like this, there's going to be something else in there. Okay? Now, the volume of a box, you guys ought to know, it's just length times width times height. So x times q. So what does q equal?
4,000 divided by x squared.
4,000 divided by x squared. So now I have, instead of a q, I have 4,000 divided by x squared. And look at that. We have x squared plus 16,000 over x, because the x canceled out one of the x's in the square. And now we have a function that we can optimize. So now that we have our function, we're trying to optimize surface area, which means it says minimized. Okay? So we want a minimum point, and minimum points can occur at either relative minimum or at endpoints. So we'll talk about the endpoints in a minute. So we're going to find the critical values using our first derivative. All right, so we have
2x minus 16,000 over x squared.
Yeah, there we go. This 16,000 over x is 16,000 x to the negative 1. So it's minus 16,000 x to the negative 2. So that's over x squared. Okay? And now we need to figure out when will this equal 0. Okay? To get the critical values. So first I'm going to get a common denominator. So if this has to be over x squared, then this is going to be a 2x cubed multiplied by x squared over x squared. And that means now that I have a 2x cubed minus 16,000 all over x squared equals 0. Now, one thing we ought to note here is what x is not allowed to equal. What is x not allowed to equal? X can't be 0. So note that. Okay. And then we can look at just the numerator equaling 0. Okay? X does not equal 0. Let's see if the numerator will equal 0. So I'm going to ignore this at this point, okay, because for a fraction to equal 0, the numerator would have to equal 0. So now I'm going to add 16,000 and divide by 2. So I get x cubed equals 8,000. And if I take then the cube root of both sides of this equation, I get x equal to 20. Okay? And our units of measure here are centimeters. Okay? Now, this is where the sign diagram can come in handy. Okay? Because realistically speaking, we already said x cannot be 0. So x actually, we also know x can't be negative. Alright? So as you're thinking about this, logically, x has to be greater than 0, but also q has to be greater than 0 as well, right? Okay? Now, theoretically, though, x could be infinitely large, and q would just be infinitely small, but never actually hit 0. So, one of the things with this problem is that there really aren't any endpoints. Okay? There really aren't endpoints in this case because x can just be greater than 0 and q will always be greater than 0 as a result. Okay? So the question is, does 20 give us a min or a local min or a local max? We have to consider that. So if I do my sign diagram real quickly here.
20 is from x, right?
20 is for x, yeah, x is 20. Okay, here was 0 that it can't equal, here's 20. If I plug, say, a 10 into my derivative, oops, I missed my prime right there, that was s prime. If I plug a 20 or a 10 into my derivative, I'd get 20 minus 16,000 over 400. Okay? Or no, over 100. So that would be 160. So I'd have 20 minus 160, which is negative. If I plug in something like 30, okay, I would have 16,000 over 900, which would be 160 over 9. What is that? That's somewhere over 17. Okay? But 2 times 30 is 60. So 60 minus whatever that was is still going to be positive. So I know that I have that for my sign diagram. And that means that 20 is a min. Okay? So x equals 20 gives us the minimum point. Okay? And then to actually find that, we need to plug it back into the original function. Okay? So s of 20 is 20 squared plus 16,000 over 20. So that's 400 plus 800, which is 1,200. And these are square centimeters again, because we're talking about surface area. Okay? So, our final answer, it says find the most economical shape. So that means we should give the dimensions. Alright? Yeah.
So was it 20 to 100?
The point on the graph of our surface area function would be 20, 1,200. So our answer is that we should make the container
And so, do we put the units? No, no.
Yeah, we should give units.
When we turn it into a point?
Well, at least in our answer, in our
Right.
final answer, yeah. Make the container with a base,
That's 20 by 20,
yeah, that's 20 by 20,
and then 400 tall.
20 centimeters by 20 centimeters. And that means we would make it how tall? 4,000 divided by 20 squared, so 4,000 divided by 400 is 10. Okay,
How did you get that?
10 centimeters tall. Because we know Q is 4,000 over x squared. So 4,000 over 400 would give us a height of 10. Okay? So that is for a minimum surface area of 1,200 square centimeters. Okay? And by the way, that, if you write out your full answer like that, then even, let's say you were reading this and you weren't sure, okay, what are they actually looking for when they say most economical shape? Okay? You're not going to get counted off for giving a little more information than they're looking for, as long as you communicate everything clearly. We're going to make this with a base that's 20 by 20 and 10 centimeters tall. That's really what they're looking for. We added in there that the surface area would be 1,200 square centimeters. So that's nice to know as well. Let's look at one other one not related to area. Here's one related to our costs. Okay? Now this also, you have to be real careful about reading the problem. Alright, so I've added a couple of comments here. And it says, when a manufacturer makes X items per day, the cost function is C of X equals 720 plus 4X plus 0.02X squared dollars. And the price function, this is where it's a little tricky, that's the price per unit, is P of X equals 15 minus 0.002X dollars per item. Per item. So that's the price. That's how much we're going to sell it for. Okay? That's not the... I've had some read this problem, they're thinking that that's like the marginal cost. No, this is the price that we're selling this thing for. So it says, find the production level that will maximize profit. So we have several things going here. Okay? How do we find profit in a company?
What they spend versus what they make minus what they spend.
Okay, what they make minus what they spend. What were you saying?
Income minus the cost.
Okay, yeah, income minus cost, revenue minus expenses, money coming in minus the money coming out. All right? So, however you think of that, that's what you've got to do. To use the language in the problem here, we'll say that the profit is going to equal their costs. Oops, sorry, backwards. They didn't use one, so I'll just use revenue. Revenue, income, whatever word you want to use, minus the costs. Okay? So, to write this as a function, our profit in terms of X is going to be our total revenue. And this I gave you because this was a little tricky. P of X is the price per item. So if we're producing X number of items, our total revenue or income is going to be X times that price per item. You know, and I should probably not use P for profit since we're using P for price. F?
Yes.
Profit. There we go. Okay. And then minus the cost. So minus that C of X function. Okay? So minus the C of X. So to flesh this whole thing out and simplify it a little bit, we've got capital F of x is going to be x times the p of x. So that's going to be 15 times x minus 0.002 x squared.
Wait, Mr. Hickson, what's the x times p of x minus what?
Cost. C of x.
Why is there an X over the P of X?
Now we subtract the cost, so minus 720 minus 4x minus 0.02 x squared. Okay? So let's combine the like terms here, and we get capital F of x equals, we've got a negative 0.022 x squared plus an 11x minus 720. That's going to be our total profit. Okay? And guys, this is maybe not exactly like this, but this is the type of thing that business people and the financial analysts and things in a company would have to do. They would need to predict how much should we produce. And they'll have different functions for costs or for income or whatnot, and they'll be able to figure all this stuff out. Okay? So, think about the domain here. What's the domain of x?
Well, it can't be.
It could be anything, can't it? All real numbers.
No, it can't be negative.
Yeah, you can have negative profit. Well, like
Well, what does x represent here?
Number of items, so items.
X is the number of items we are producing. Okay? So yeah, so the domain here, x has to be greater than 0. Is there a cap on what x would be?
No.
No.
Well, I mean, if the profit is equal to 0.
Okay. And profit, well, actually, if the revenue equaled 0. Okay, and what would make the revenue equal 0 is if the price that we were charging was 0. Okay, so there's the other end of the spectrum. We wouldn't want x to get up to where we weren't charging anything. That wouldn't make sense. So if we do 15 minus 0.002x equals 0, then 15 would equal 0.002x. And if I divide, that's going to make it 7,500. Okay, so x has to be between 0 and 7,500. Okay? Now, think with me here. What shape is our profit function?
It's a parabola.
Huh?
If you include the whole domain, if there's no domain, the domain is parabola.
Yeah, that function's a parabola. Alright? So, are the endpoints, and notice what's the leading coefficient? It's negative. So our parabola is going to look like this.
So there's a minimum? Alright.
Okay? I don't know why this won't write for me. Okay? Yeah, it's going to be a parabola opening downward, so the only critical point we should get will be at the vertex. Okay? It'll be right at the vertex, and the endpoints will be lower, of course, because the vertex is the maximum. Alright, so let's go on and do this part. Alright, we've got f prime of x is a negative 0.044x plus 11. Okay, so there's our derivative. And now we set that equal to 0 and solve it. Okay? So this equals 0. So 11 equals a positive 0.044x. If I divide, that's gonna be 1,000 divided by 4, which would be 250. Is that right? Someone help us out.
What's 0.44? Yeah.
11 divided by 0.044?
Yeah.
250? Alright, good. Okay, so now somehow we need to test the endpoints, the critical values, and any points where the derivative is not defined. Well, this is a linear derivative, so it's defined everywhere. So we don't need to worry about that. The endpoints we already said, because this is a parabola, our critical value is going to be right there. So guys, here's where you can save yourself some work by remembering things you've learned in the past. Okay?
Is 250 the critical value?
So 250 is our critical value. So let's see what f of 250 equals. Is 655. So our maximum profit, okay, all right, they make a max profit of $655 a day, okay, $655 if they produce 250 items a day. Now, okay, as for the production level, so that's what we're doing there. They could maybe ask for the price, you know, how much would we be selling it for at that point? But you could figure that out easily, just do 655 divided by 250, or plug it into your price function up there at the top. Okay? I think that would end up being...
Which function was I just supposed to use? I'm so confused.
What?
Which function was I just supposed to?
To get the 655?
Yeah.
F. We're trying to figure out, notice this is the critical value of F, so right here.
Yeah. Oh, I didn't. Oh my gosh, I didn't put the 720. Sorry.
Oh, okay. So you got like 1,275?
Yes.
Okay. Alright.